Hello and welcome to our webinar from the virtual event series of DECICE project. My name is Alexander Nikolov and I'm working for Senior GmbH based in Vienna, and we're coordinating the dissemination communication exploitation work package. The purpose of these online gatherings is twofold. Firstly, we seek to disseminate the valuable knowledge we have acquired during our project. And secondly, we seek to engage with a broader network of interested parties. We aim also to gather more insights about the unmet needs and potential areas for innovation within the sector and incorporate this new information into our ongoing project. Within the next 90 minutes, we'll introduce the DECICE project to the audience and provide concise overview of some of its relevant actions. The agenda will continue with a contribution by Mr. Sebastiano Mengozzi, representing the University of Bologna on a specific use case of DECICE, showcasing practical applications and outcomes. Next, Mr. Lorenzo Moro from the Top IX will introduce Fluidos project, its framework, objectives, and contributions to the computing continuum. Last but not least, Mr. James Phillip from the European Digital SME Alliance will share some insights into the Fluidos Open Call, exploring opportunities for collaboration and project participation. The event will culminate with questions and answer session, to which we kindly invite all participants in the webinar. Finally, the webinar should end at around 1:30. So next slide, please. So before we continue with our today's agenda, I would like to highlight our today's housekeeping rules. Namely, our virtual event will be recorded and posted on the DECICE project website in order to ensure, according to the rules of open access scientific information, that all collected insights are openly accessible for all interested parties and can support further development activities in the field. Feel free to ask questions anytime in the chat option. We will do our best to answer them during the events, and if you would like to speak after each presentation, please raise your virtual hand. That being said, I would like to pass the floor to our co-host, Mr. Christian Recca from Top X. Christian, the floor is yours.
Okay, thank you. Thank you for having me. Thank you to all the participants for being here, and thank you, Sinio, for hosting this online session. Yes, my name is Christian Racca. I'm a program manager at Topics. We are a non-profit consortium based in Italy, in Torino. Our main business is the internet exchange, so our focus is on network interconnection, but we have a second business unit named the development program, where we are pretty active in different spaces like data, entrepreneurship, innovation, and of course some funded projects. And in fact, two of the projects where we are currently involved are definitely Fluidos and DECICE. So we suggested this joint session today in order to explore the computing continuum topic from two different point of views. In the next few slides with the presenter, we will address this topic, but let me share a couple of slides in order to create a bit of context around this topic. I'm not sure the old people here are aware of what is computing continuum, so I have included a very basic definition. And according to this definition, the computing continuum refers to a seamless and integrated, and these two objectives are pretty important, infrastructure to connect cloud computing, edge computing, Internet of Things, and the idea is to enable data processing in order to happen across different layers and from the centralized spot to the edge of the network. Well, I mean, this definition is again is pretty synthetic and basic, but you can see how much it is dense of information. So a lot of concepts. We have cloud, we have edge, IoT, we have computing resources, we have the centric versus the edge approach. So it mixes together many aspects and many layers of information. Computing continuum is quite critical right now for European community, and in this slide I try to summarize why it is so important. First of all, it is it is a matter of digital autonomy and digital sovereignty, two words that are in the, let's say, EU agenda in the last few years. You know better than me than big cloud hyperscaler are not from Europe, unfortunately. So we are trying to fill the gap, or to create our knowledge and our skills, our position as Europe. And I mean, participating in this project is a way to contribute to this mission. It's also a matter of economic and industrial competition, because having the data more close to the final users and having infrastructure more resilient and robust is a way to provide better services to the final users. So again, it's about the competition and the market. It's also about the sustainability and energy efficiency. We are infrastructure guys. We know pretty well the importance and the impact of ICT on the environment. Well, and not always a positive impact. So a better and a more efficient usage of resource contributes to this energy efficiency topic. So let's say we are contributing to this aspect. Of course, it's a matter of resilience and security. Having these data that are not all centralized in one single spot, having this robust and resilient network, it's a way to make this infrastructure more tolerant to fault, to attack, or to technical issues. And of course, we are in the space of the research, so we are speaking about innovation, potential new business models, and we can't let's say we can't skip to consider the AI topic out of this space, because it's pretty interconnected. It is also interesting to see how much or how European community is addressing this topic through the different funding programs. We had Computing Continuum in Horizon 2020. We have Computing Continuum in Horizon Europe, and we will address this topic in the future, of course, with different directions, different priorities, but again, we are always talking about Computing Continuum. And it is also important to understand how much funding European community is putting in this space. For instance, we have about 100 million on the topic of meta operating systems. That is probably where Fluidos is located as a research project. About 50 millions in the field of cognitive cloud, where DECICE is positioned. Then we have open source for cloud-based service project with other 25 million. There is a strong connection with Simple, this big open source smart middleware platform that is just started in the operations. And of course, there is a connection with the important project for common European interest, where other millions, other billions, better, are allocated for projects. So a lot of money, a lot of importance. And as you can see in this slide, I try to put, let's say, most of the projects that are in these spaces. You can see here in the slide also DECICE and Fluidos that are part of this ecosystem. We have funded project. We have some, let's say, initiatives like Gaia X, for instance, pretty active in the field of cloud trust and standardization. We have other federation private initiative. We are also connected with this Fulcrum project initiative. So I mean, lot of players, lot of actors. It's a pretty crowded scenario and a vibrant community. Well, This concludes this first very brief presentation. Hope it was useful for you to stay connected to this topic. Now I would leave the floor to Mirage from GVDG, one of the, let's say, main partner in the DECICE project.
First of all, welcome everybody. My name is Miraj and I will briefly present DECICE project today. So first of all, I would like to show our consortium and general project information, and then our heterogeneous compute continuum and what kind of challenges we have and what DECICE offer to those challenges, and lastly, our future work. So let's start with basic project information. We started our project in November 2022, and our project duration is 36 months. And project will be ending next year in November. So our project lead is University of Göttingen. The principal is Professor Dr. Julian Kunkel, and the contribution is around 5.6 million. So we have 12 partners right now, project partners, University of Göttingen, GWDG, E4, KTH, HLRS, Huawei, Big Tree, Sinio, Marmara University, TopX, Unibo, and NAC. So let's continue with the heterogeneous compute continuum. We generally refer this term if our compute continuum is including different type of resources, for example, HPC, cloud, edge, and IoT. So, of course, if we have different resources and users generally have different computation requirements and storage requirements. For example, user may want to train a model on a powerful GPUs with a bunch of data, and maybe they need lots of storage spaces in terabyte level. So we have to schedule those jobs on HPC environment instead of edge or cloud environment, or vice versa. If you want to collect some data from IoT devices, you cannot schedule these jobs on HPC. Yeah. So what kind of challenges we have here? As I said, the most important one probably job scheduling. Our project is based on Kubernetes for orchestration platforms. So Kubernetes scheduler does not natively support HPC scheduling. That's why we are trying to intervene these processes. And also Kubernetes does not know locally stored user data. Of course, it knows if we download container images and if that image is present on the machine. But what about user data? It doesn't know. And also, we have performance issues. If we want to schedule any job, to dependent job into distant location, your network, you will have network problems, especially in bandwidth, latency, and throughput. So what DECICE offers to these challenges? Let's talk about this. So as I mentioned, our top priority is scheduling, efficient and energy efficient and compute efficient scheduling. So what we are offering is AI compute scheduler. It's basically improving job placement on different resources, compute resources, and improving the utilization. For data locality, we are also offering AI storage scheduler. Basically, this one is checking time series data and improving data placement decisions. For performance and availability, we are offering dynamic digital twin. It's basically a digital replica of the system supported by the system metrics. It's collecting lots of metric data from different resources and processing those information according to our needs. So I would like to briefly explain the architecture here. We have compute plane including different type of resources, for example, HPC, cloud, and edge. And as you see, we have kubelet agent. Let's call them agent, Kubernetes agent for now. And every node basically has this agent and connecting to our DECICE framework. And also for edge devices, we have Edge Core regarding the extension of Kubernetes. So we are interacting with this platform via our glue code in DECICE framework. The center of framework is DECICE Control Manager. It has lots of API, so we can trigger job scheduling, we can get telemetry information, or we can check the status of compute plane, and also we can provide some certain aspects of security. And the core component of DECICE framework is DECICE model. It includes digital twin, scheduler, controller, and AI scheduler. We basically have three type of scheduling processes. The most important one is, of course, AI scheduler. As a fallback, we are trying to include gang scheduling and also lots of scheduling strategies. So let's continue with the digital twin. This component is very important for the framework. So basically, it provides the presentation of the current system status, and it's collecting data from different resources, but mainly from Prometheus, which is time series database and monitoring system in our framework. And also it gets data from different APIs and our virtual training environment, which I will explain later. And after processing this data, it saves this data in different time series database, which is InfluxDB. And this data can be accessed by different digital twin clients, let's say AI scheduler or virtual training environment. And also we have machine learning modules to predict anomalies and also energy prediction, carbon dioxide emissions as well. In our virtual training environment, the main purpose is simulating different operational conditions and scenarios, because training your AI model on real-time systems takes lots of time. So we are trying to create different scenarios. For example, we are injecting node failures and network failures, and we are trying to train our AI model. So this basically reduces the costs and risk of real-world training. And lastly, our AI scheduler, we are trying to improve Kubernetes job scheduling, and also it's interacting with the Kubernetes API, basically providing job and node mapping. Basically says this job must be scheduled on this node or that node. So it's getting the data from digital twin, and then doing all the magic inside AI schedulers and different scheduling algorithm, and sending these results to the evaluator, and finally calculating this score with wrapper. And then output of this AI scheduler is a mapping between jobs and nodes. And lastly, I would like to talk about our future work. So right now we are trying to improve our AI scheduler and digital twin, and also we are almost integrated our AI data scheduler and compute scheduler, AI compute scheduler, which is called integrated AI scheduler right now. We also almost integrated all of these components, but of course we have to do end-to-end tests to release some kind of prototype. Let's call them minimum viable product, MVP. Yeah, our target groups are cloud to edge operators, HPC and enterprise data center, academic and research institutions. As you remember, we have lots of academic researchers in this project, and we are trying to contribute scientific community. And also we would like to provide this product to cloud and HPC designers, and lastly, system software developers. Yeah, as a summary, we are developing open and portable cloud management framework, and it is AI based, and it is improving scheduling decisions in orchestrating platform. Also, we are providing synthetic test environment to support AI models and train them in realistic scenarios. And lastly, we have dynamic digital twin to present the current system and provide the formatted structured data for AI scheduler and different components. If you want to get more information about the DECICE project, you can visit the website, you can contact us, and you can follow us in different platforms, social media platforms. Thank you so much for listening. That's all from my side. If you have any questions, I'm happy to answer.
Thank you so much, Mirak. Very, very precise in your presentation. Of course, if there are questions, please go ahead in the chat, or we have the final Q&A session at the end. Let's deep dive a bit more in the use cases of the DECICE project. Honestly, we have 3 use cases listed in our project space, and we decided to present one of them to them today. So I would invite Sebastiano to join us in this discussion. Sebastiano, are you here?
Hello, everyone.
Ciao,
Thank
ciao.
you for
How are
having
you?
me.
Yes, we can hear
Fine,
you
thank
pretty
you.
well.
Yeah.
You should be able to present yourself, your screen. Otherwise, we can do the same as Mirak. But let's try with your presentation. Good. You can, yes, just put in full screen.
Are you able to see the full screen presentation?
Still seeing not the full screen presentation right now.
Okay. So I should have selected it, but maybe if that's not the case, we would go for your presentation, maybe.
Okay, no problem.
It should be full screen.
No, still seeing let's say, no problem. I would share my presentation here.
Okay.
Here we are, and
thank you.
Here you
Thank
have
you so
your
much.
slides.
Okay. Good morning, everyone. I'm Sebastiano Mengozzi. I'm a PhD student at the University of Bologna. And in particular, we are developing the use case 3 of the DECICE project we titled it In the Field, Intelligence Supporting for Emergency Response. So I will go briefly give you an introduction about which is the goal we want to achieve. Then I will explain to you what we imagine as a use case scenario for this new technology that the site is developing. And I will briefly introduce you to the software architecture that we are developing. And finally, we will sum up with some benefits that the DECICE framework can give us. So let's start with the introduction. So our goal is to apply the DECICE digital platform for targeting emergency response activities and using as a support for emergency responders autonomous drones. So which challenges we have to face? We have to achieve safer autonomous navigation because we want that the drones are fully autonomous. We need to fuse the intelligence data with the data that the drones can gather from the field. And finally, we have to orchestrate multi-agent and multitask framework. So that's why we need DECICE for this application. So how do we want to achieve that? Using flight control algorithms that can run on board drones in real time. So these drones can capture the data from the field with onboard sensors that they carry on. And then we can process the data that they have gathered in the field in the edge directly, or move them into the cloud and then process it on HPC, depending on, for example, mission conditions, such as the latencies that we have for the response time of our data, or the battery life that is left on our autonomous drones. So regarding the scenario that we imagined, we divided our emergency response scenario in these three main aspects. So we have a mission definition phase in which we use intelligence data to define the mission that we have to perform with the drones. Then we use a planning phase to actually organize which goal the drones have to achieve using also the information that we get from the field. And finally, our operators are the autonomous drones that actually are in field and can move around autonomously. From a more technical side, we need to test this infrastructure first in simulation. So for this reason, we are using a Pix4 flight controller that is a common, well-known flight controller in the community that is open source and open hardware. And we can run that in software in the loop. And we leverage a physical simulator, in particular Gazebo, that can produce synthetic data from simulated drone flights. And this physical simulation actually is not something that is taken into account from the DECICE framework, but it's just a proxy for the reality, so to test our algorithm without crashing anything. And also we use the robot operating system that is a common framework to develop autonomous robots applications, also in the industry. And when you use that to run our algorithms and process data. So which software we imagine a software architecture. So we have like the first image processing node that can, for example, receive data from satellite images from a disaster zone or where you have to intervene. And in this image, we can outline some region of interest. So areas in which responders want to explore or want to gather data. And maybe the objective could be to find survivors or to find riverbanks damages or wildfire sources. So depending on the scenario we are facing. And then we have to forward this information about the region of interest to the other computing platform. So that a mission can be outlined for the response operation. So then we imagine a mission planning node in which this data is gathered, also fused with the information coming from the field. So, for example, the drone position, the drone battery status, and using that data, we can plan a mission optimizing some metrics. For example, we want to minimize the total path length that each drone can travel to reach a goal so that we can respond faster and we can also save battery. And also we can use the data from the field to replan a mission. Maybe we find out that a region is not so interesting, so maybe a drone can be rescheduled to move into another point. And finally, we go, this is more a control algorithm that are related more to the edge since we have the real-time constraints. So in particular, the flight control algorithm take care of arming the drone, taking off, landing, and also controlling it through a trajectory to reach a desired goal or a desired target. While also we can run on the edge or maybe offload this computation to the cloud, more high-level algorithms to, for example, process the data that comes from the field. And we can also use that data to send feedback to emergency responders. And our edge devices is composed by high-end sensors, for example, cameras, and small computers that are really powerful but can also are small enough to be mounted on a drone and carried around. And also the flight computer that takes care of stabilizing the platform and use the low-level sensors to estimate the orientation and the position. So which benefits we can get from the DECICE framework? Next slide, please. So thanks to the intelligent scheduling, so we can use this AI scheduler to customize the scheduling, particularly for our use case, and also maybe schedule jobs in terms of the energy that we have at disposal on each platform. And thanks to this, maybe we can optimize the mission duration, and so we can explore many areas and get a better outcome from the mission. Or we can also leverage the computing continuum to for robustness. Maybe we can lose at a point a drone for a crash or because of the battery dies, and then we can respawn the task of gathering data into another drone. And finally, we by collecting data with the edge devices, so our drones, we can then forward this information into cloud devices, and so we can process them outside the edge devices and collect them. So that's a brief introduction to our use case. Thank you.
Thank you so much, Sebastiano, for your presentation. Pretty happy for this introduction. To be complete, in our project in DECICE, there are other two use cases. One is managed by Maroon University in Turkey, that is about the autonomous vehicle management, and the other one is about the MRI images processing run by our friends in Göttingen. And these these are the, let's say, the test beds for our DECICE framework. Now I put in chat also some additional links for deepening our project, and I would ask instead to my colleague Lorenzo, that should be here. Lorenzo, are you there?
I am. Hello.
Yes. How are you?
Oh, fine.
Okay, thank you, of course, for presenting Fluidos project. We introduced DECICE as the first project today, but again, this is a joint session, so the idea is to have and to present a second approach to the computing continuum from a different perspective, more focused on the meta operating system, and now is the time to see and to discover more about Fluidos. Would you try to share your screen? In this way, you are independent in moving the slides.
I will try. Let's see if it works.
It
Can
works.
you see it full screen? Okay.
Yes. Perfect.
Good. So, hello everybody. I'm Lorenzo from Topics, and I'm here to represent, or at least give you a brief introduction about the Fluidos project. And that's it. So, what is Fluidos about? As the name suggests, it's a decentralized operating system with some properties: flexible, scalable, secure, and many more other properties. So we have a traditional approach here when talking about computing continuum, as Kristen pointed out at the beginning, and also we have seen in the DECICE presentation. So the traditional one is about silos, right? So we have the edge, we have the very edge, we have the cloud, and when we want to deploy some applications on a computer, let's call it computers in a general way, we have to design it with taking into account the platform that will take care of making it run, right? So if it's about the edge, we have to design it in that way, taking also the constraints about that one, the edge availability and machinery and so on. And if it's working on the cloud, it's running on the cloud, we have to do something completely different sometimes. So the scope, the main scope of Fluidos, and let's say the objective is to to unify these silos. So not taking them just like different aspects, but creating a real continuum and helping the user to create and deploy applications without taking care of where actually they will be deployed. So, as I just said, this is the new approach we are trying to foster. So from a traditional one, where we have application with several components and each component is deployed in a different silos, let's call it, from per edge to telco edge. For instance, per edge, we can say about the robots or sensors or cube edge applications we will see later. Telco edge could be the edge nodes in the regional and metro area where telco operators deploy the routers or aggregation routers, for instance, and the cloud is the main data centers. We all know that. Fluidos abstracts this division, right? So we have this computing continuum layer. We'll see later how it is made up. And all applications are deployed in this layer. So the fact that they are actually run on the far edge or, for instance, in the cloud, it's a matter of orchestrating those workloads, taking into consideration a lot of constraints and boundaries, some made available directly by the owner of that application, and some collected from, for instance, the energy aspects or the telemetry services and so on and so forth. So it's about basically transparency, deploying transparency. So we're deploying to a middleware where everything is working. We have a communication transparency since the interfaces and the lower bounds are the same, and we have a resource transparency since each resource is modelized in a standardized way. Then this is the stack of Fluidos. So this is briefly, of course, the architecture is a little bit more complex. We'll see it later for some aspects, but the stack is here. So we start from a hardware layer where we have the physical devices, and each physical device could be, of course, a different kind of platform. So from embedded devices to robots to on-prem servers, real-time devices, and so on. And each of these other platforms runs, of course, a vanilla operating system dealing with the kernel and all the, low-level features of that hardware platform. And this is, of course, different from platform to platform. Then we have this Kubernetes layer, which is homogeneous. So Kubernetes is the baseline that is common to every kind of deployment of Fluidos, from the very edge to the very cloud. So, of course, Kubernetes can be vanilla Kubernetes, could be K3S, which is it's been designed for resource-constrained devices. Could be also other cloud orchestrators potentially, but at least Kubernetes is the baseline. On top of Kubernetes, we are running Fluidos as its own software, and Lyco. Lyco is a technology which has been developed by the Politecnico di Torino here in Italy that is responsible for creating the actual continuum. So basically, it helps extending a Kubernetes cluster, borrowing resources from another cluster of another tenant, without making it without changing the way of those resources are engaged. So basically, the owner of the cluster, which is borrowing resources, sees a virtual node in its own cluster like it was an actual node in that cluster. But this is just a shadow of the real node, which is borrowed from another cluster elsewhere. And Lyco is dealing about creating the tunnels that let the data pass from one cluster to the other one, and also the resource engagement and reservation. So Fluidos is about these technological pillars. So we have the node and the protocols, which are the base core software of the project. Then we have the meter orchestrator, which is the module taking decisions. So the algorithmic part lives here. We have the security aspects, which are, of course, by design, widespread across all the different modules and software components. Then we have all the energy reasoning and inputs to the node. And of course, it's an open source project. So we will see what kind of technologies we've integrated. So this is about the node. From the left part, we are seeing a brief and a high-level overview of the architecture. I'm not going to really deep on that because we don't have time, and it's not also I think the right place to do that. But what I want to communicate is that Fluidos runs on pods in a Kubernetes cluster. So it exploits Kubernetes metrics, it exploits Kubernetes APIs and Kubernetes way of creating and managing resources. So we have these pods that are running controllers, so exploiting the Kubernetes controller pattern, which is a kind of pattern that is really helpful when dealing with the custom resources, which are a kind of data structure that Kubernetes is working with. So we have these modules running on pods, running on a Kubernetes cluster, and we have gateways, that is to say, components that need to speak to their homologous components in another cluster. And the language they're speaking is based on HTTP, of course, but is exploiting a newly born protocol. We call them REAR, which is Resource Advertisement and Reservation Protocol, which basically deals with the retrieval of the flavor. The flavor is basically the description, semantic description of resources and services made available by one cluster provider to the whole Fluidos ecosystem. And then we have the other phases of engagement of those resources, so the reservation and finally the purchase. And this is all dealt by REAR protocol. And after REAR has completed, and so we have a purchase actually done, even though there isn't an actual economic, let's say, money transfer, I would say, but I mean a technical purchase in that sense, then LICO can start creating the continuum, and finally the resources could be deployed. The workload can be deployed. Please bear in mind that a Fluidos node is a Kubernetes cluster, not a Kubernetes node. So it's called node in the same way, but we are referring to different aspects. The meter orchestrator is that module that is taking decisions. So basically, it's a software component that takes into, as an input, an intent describing an application that the user wants to deploy on Fluidos. And the description of this application could leverage several descriptive languages, for instance, MSPL, or could be native Kubernetes or model by Kubernetes and so on. And based on the syntax of those intents, there are different orchestrator, for instance, the MSPL-based meter orchestrator or the model-based meter orchestrator, which are running as components in Fluidos as well. So they are basically pods as well, that taking this intent as an input are basically looking for a place where this application can be deployed. If we have the resources available in the local cluster, so where the intent jumps in, because they are already available and they're matching the intent descriptions and attributes, that's fine. Otherwise, we have to solicitate the REAR protocol and all the Fluidos node components to retrieve these resources from a remote cluster. So looking at possible clusters, asking for flavors matching these intents, engaging those resources, and finally deploying the workloads. Every aspect of the workflow is secured by design. So authentication and authorization, integrity, of course, and so the classical security properties are enforced by design in every aspect of those processes, also based on the kind of threats that each phase could face. So in discovery, resource acquisition, usage, and so on and so forth. Every aspect is taken into account, of course, from some software tool, open source software tool, of course, or a specific methods or algorithm, protocol whatsoever to enforce this. Some other words about energy. So the fact is that, as we said previously, energy is the baseline for all new technologies that come here in the cloud world. Since it's a constraint we have to take care of course, and in Fluidos we designed everything with energy in mind. So we have a whole work package thinking about this. Of course, AI in the recent years becoming let's call trend topic also for the general public, has raised interest in that. And so we are approaching this matter in Fluidos, of course, following two different paths. So one path is to reduce the embodied carbon, that is to say, the carbon footprint of machineries that are working, that are just powered, right? So just by powering them. And we solve this by using less infrastructure, so increasing the utilization rate. And that's what Fluidos has been designed for at the very beginning. So basically exploiting available resources where they actually are, right? And so increasing the utilization rate. And this is to reduce the embodied one, so the one you can't really control, because if a device is powered, it will consume. The second approach is to reduce the operational carbon, is to say, to take decisions which could be triggered by AI predictions or load shifting based, for instance, for the renewable energy availability from time to time during the day. Let's think about, for instance, wind or sun and so ever, to input this data to the meter orchestrator so that they can take decisions based on those metrics and shift the workloads and running applications on the place where, for instance, energy in that moment is more available or more economic from one point of view, right? So this is the multidisciplinary approach, we would say, about energy. Of course, everything is open source, so we are using open source technology where they are already available. Kubernetes, as I just said, K3S, Lico, KubeEdge. KubeEdge, for instance, is an interesting part about what the edge part and edge world will be, for instance, the sensors, right? I've been taking care into Fluidos, so we have people working on that, of course, and every software we have been developing is, of course, open source, and these are the types. We have three flagship use cases from the very beginning of the project, and then, of course, we have other use cases coming from the open calls, but James will go deep on that later. These use cases are about the smart viticulture, the intelligent power grid, and the robotics logistics. And while the first two ones are basically related to the fact that, the first one is about deploying the services just like some in the cloud and some on the edge based on where in that moment we have necessity. The second one is about resiliency, because the applications that are getting metrics and data from the smart grids need to be really resilient and the high availability design. And the third one, the robotic use case, is about exploiting robots that are not currently operating, so basically moving, but just charging, for instance, to the charging station, to run workloads that could be battery draining for, instead of those robots that are actually operating and so moving. So just optimizing the energy and the battery availability in a facility, right? This is more or less the three use cases. So these are our links. I hope that the presentation has been clear. If you have questions, of course, raise your hands or write on chat. And thank you so much.
Thank you very much for inviting me to the webinar. My name is James Philpott. I am a project manager at the European Digital SME Alliance, and within Fluidos, we are the open call managers. So we are responsible for organizing this process. So to begin with, I will just take a brief step back and explain what are open calls, because these are kind of a pretty unique concept to European projects, so maybe not everyone is aware. They come under different names. They can also be called cascade funding or financial support to third parties or subgrants. These are all the same thing in that it's money distributed from a European project to a third party external to the project consortium, with the idea of funding a specific task or activity for a short term within the project lifetime. And the idea is that this awarding of the grant helps achieve or demonstrate the project's viability or work towards the project goals. So within Fluidos, we have already held one open call that's currently running, so we are halfway through that period, and we have a second open call process that is receiving applications at the moment. And so we are using this open call to validate our technology. So we are awarding use case grants. And so this is done through either awarding individual applicants or small consortia, so up to 3 entities, a maximum amount of 120,000 euros to take the FluidOS system, deploy it within your domain and with your systems, and then validate and evaluate how well it runs, test the functionality, and then report back to us the results. So this is done in an 8-month period. So the idea being that the use case grants will be begun in December. And the application should set out the kind of goals of the integration, some targets, and then these are measured over that period with the kind of monitoring of the project partners as well, and a couple of reviews to make sure that everything is going well. So the practical details, very importantly, the deadline is a week from today. It's the 4th of October. The applications close at 5 o'clock Brussels time. And to apply, you need to fill in the application form that's available on the platform, which I'll link in a moment. So this application form, it sets out your concept and your idea of how you will use FluidOS, how it will integrate with your systems, and most importantly, what the benefit will be to you and your work of using FluidOS as opposed to the kind of current way that things are done, and then how you can measure this benefit. So alongside this application form, you also need to sign a declaration of honor, which is simply a form that says that if you are selected, you agree to carry out this work. And if you are an SME, we need to know that you conform to the EU definition of an SME, so there's another form for that as well. And so just to confirm that it's an 8-month period that the grants will be awarded for, this will start in December. You will have support through a project mentor. So this is one of the project partners that works in a similar sector, and you have ongoing dialogue with them, but then also as a project as a whole with the technical coordinator, we have a couple of periodic reviews to check the process. As I said, we are looking for use cases and different demonstrations and validation of FluidOS. And so part of this is making sure that it's not duplicating something that's already been done. So Lorenzo mentioned the 3 pilots and use cases within the project, but we also funded 5 use case grants in the previous period. And on screen here, you can see some of them, and then the next slide shows the rest. And I'm not a technical person, so I won't try and explain what these are doing. But there's more information on our website, and also I think the slides will be shared, so you can check here to make sure that there's no overlaps. Because the point of no duplication is not that we won't accept applications that are to do with smart viticulture or robotics. It's the functionality within that. So even if you are working with robotics, if your suggested use case is doing something very different to the ones that we're funding or the ones within the project, then that's absolutely fine. But if you're doing something that's already being tested, then this is something that will be part of the evaluation. These are the other 2. As I said, the slides will be shared, I think, so that you'll be able to see these in more detail, and also it's available on the website. But just briefly, to give some advice for applying, we have on the application platform all of the project deliverables, all of the publications that explain the technology of FluidOS, how it works, and what we're trying to do. So reading these will help you understand how you can integrate your system with ours and also achieve what you intend. On the platform, there is a guidelines for applicants, and this shows you the evaluation criteria that will be used to score your application. So this can help you write a good application that's targeted to what we want to see and what will be evaluated. A really key point, as I mentioned, is to demonstrate the value of FluidOS. We want to know if our system is working and how it can help users. So the application can be structured around demonstrating what value FluidOS will bring to you. So that's why I said, check the existing use cases and pilots, because duplicating something that's already being tested will be part of the evaluation. And finally, if you are integrating into your own software, it's really important to make sure what this is and how it works, because the evaluators won't be reading outside of the application. So all the information needs to be contained in there so that they don't have to go searching or make assumptions. If you have any other questions, of course, I'm here on this call, and we also have a kind of helpline as well. So please feel free to reach out to us, and best of luck with your applications.
Thank you so much, James. Pretty clear. Just as a matter of curiosity, given that we finished our presentation, do you have any insights about what apply to the first open call? I mean, in terms of, let's say, countries in Europe. I mean, you get application from all around Europe or from some specific countries?
We did. We had quite a nice spread. So we had 50 applications last time. I think it was Spain and Germany that actually had the highest levels, but we also had several from Greece, several from Italy. So there was quite a range of applicants, which was nice to see.
Good, good. Thank you so much. Thank you so much. And with this presentation, we concluded our panel of speakers. So, yes, there is a question from Sachin.
Yeah, unfortunately, UK applicants,
precise.
they aren't eligible because the funding that was received for this project came from a previous funding round from the EC. So it means that even though the UK is signed up to Horizon Europe again, when this project was funded, they weren't, which means that UK applicant can't be funded. If they are working with European entities and none of the budget would go there, then they could be considered, but they can't receive funding from us, unfortunately.
Thank you. Any other questions from our audience about Fluidos or the DECICE projects? Let me check in the. Yes, thank you for sharing also the application form. Pretty useful. Don't miss the deadline. That is 1 week behind, more or less, because it's October 4, right?
Exactly.
Good, good. Okay. Let me also invite Alexander again, if he is still connected, for joining me for the final, let's say, conclusion or bye-bye session, let's say.
Thank you very much, guys, for joining us today and participating in this wonderful webinar. To remain in contact and be informed on any related exciting activities from DECICE, please visit our project website, which was posted into the chat option, or follow us on our social media, LinkedIn and Twitter accounts. Thank you very much for joining us today, and wish you a nice rest of the day.